Hello everyone, welcome back to Term 2 for MEM 23006A Apply Fluid and Thermodynamics Principles in Engineering. Before we start, I would like to read a quick disclaimer. This online recording is intended for internal teaching within South Metropolitan TAFE, Carlisle WA campus only. You may not either directly or through the use of any device or other means copy, download, upload, publish the content unless expressly permitted by South Metropolitan TAFE in writing. So welcome back to Term 2, Week 11. And thank you for everyone that have submitted the draft report. I will reply to your draft report uh, in your individual email. What we're going to discuss in term 2, so we departing from heat transfer as we discussed in term 1. In term 2, we'll focus our lessons to perfect gas as well as fluid static. So as you know, in term 1, there is a heavy subject on thermodynamics. In term 2, it's going to be a heavy subject on gas processes, mainly internal combustion engine, probably on four-stroke or diesel engine, one of another. So for the week 11, today we going to discuss a perfect gas law. If you have a book, which is the same book we use in term 1, thermodynamics and fluid mechanics, an introduction, we are on chapter 5. What I'll do, I will post or scan some of the examples and I will put it in the Dropbox, but I will um, display the questions inside this recording as well, just for your information. Now, let's have a look general gas equation. So the purpose for this lesson today, we're going to discuss a perfect or ideal gas. We're going to also discuss a couple of gas processes such as constant pressure, constant volume, isothermal, polytropic, adiabatic, which is you're going to see later on. Now, why we discussing this perfect gas? Well, this perfect or ideal gas is sometimes defined as a one that obeys the gas law, which means the molecule of gas occupy a negligible volume compared to the volume of the containing vessels. Or you can say the molecule move independently of one another except when collision occur. There's an energy transfer in or out of the gas, which is caused in the molecular linear kinetic only. Now that probably doesn't mean much to you, I know. I just read it from the textbook, but that is what the definition of perfect gas. What we're going to assume for the perfect gas is monoatomic gases such as helium and argon, diatomic gases such as nitrogen, oxygen, and carbon dioxide, as well as gas mixtures such as air that we breathe now. But refrigerant or vapors or steam, they are not classified as perfect gas. So for refrigerant, you have to look on the refrigerant enthalpy chart to see what's the properties of that particular refrigerant. Same with the steam, you have a steam table that define the properties of the steam at each pressure and each temperature. So the gas law, what we have here, what we call general gas equation. is defined as PV over T equal to constant, or you can say P1 V1 over T1 equal to P2 V2 over T2. This is what we call general gas equation. So pay attention here. The P here stand for pressure, and the unit is Pascal. The V here stand for volume. The unit is cubic meter. And the T here stand for temperature. Now, in gas equation, we use absolute pressure, I mean absolute temperature. So we will use Kelvin. Now to convert from Celsius to Kelvin, what you need to do is whatever the degree Celsius is, and then you plus 273. Same with pressure in here. We are going to use absolute pressure. So you have to add 101.325 kPa or 101.325 Pascal. So please pay attention to the unit. I know some of you struggle with the unit from the first term. There's a confusion between kilopascal and Pascal. So in this case, if the pressure that you work out is on kPa, please convert it to PA, or if you want to convert to absolute pressure first, you add 101.325 kPa, then multiply by 1000 to get Pascal. But it's already in Pascal. You just add 101,328 to 325 Pascal. Okay, so that's what we call general gas equation. The next equation that governs a perfect gas law is what we call equation of the state. So it's given by PV equal to mRT. So this is what we call equation of state. As before, P stand for pressure, V for volume, T for temperature, M here stand for mass of the gas, and the unit is kilogram. The R here stand for gas constant, and the unit is joule per kilogram Kelvin. R is normally given in many handbook, but if you have to find the R, the formula is 8314 over M, which is M is relative molecular mass, no unit. So don't worry too much with this R. In your exam it'll be given, and then please also check your formula sheet for term 2. So there's a couple of R value for common gases. So this gas equation only apply for perfect gas only. So as discussed, is for monoatomic gas like argon or nitrogen. It can be for, helium and argon. Nitrogen is diatomic gases. Um, Oxygen, carbon dioxide, and of course the air that we breathe, which is consisting of a mixture of many gases. Now, how does this relevant to HVAC? Let me erase this verse. If you look on this picture here, so this is the project at SMWC where I was the project designer or project engineer for this particular site, which is St. John of God, Murdoch. So we did upgrade one of the medical center, and then it consisting of many VRV condensers. What happened is, because this condenser serving multiple floors below, sometimes 5 floors below, we want to absolutely sure when the subcontractor did the bracing on the copper pipe, there is no leaks. And if there is a leak, you have to find it before all the ceiling and the riser is closed. To do that, what you have to do once they finish with the bracing and connecting all the copper pipe back from the condenser to the fan coil unit at the floor below, we pump or we pressurize the system with nitrogen, as you can see here. So we put the nitrogen into the system and we pressurize it to about 3,800 to 4,000 kilopascal for 48 hours. If after 48 hours the pressure remain the same, then it's all good. The system can go into vacuum, so we hold for a couple of 100 micron for 24 hours. If the vacuum hold, means the system is leaks free. Then they can start charging with the refrigerant gas. Now, how the perfect gas law relevant? Well, say for example, you come to pressurize this system at 7 o'clock in the morning. So the subcontractor was on site 7 o'clock. They pressurized the system. 7 o'clock in the morning, you come and witness. Yep, you took the photo. It's about 3,800 kPa. And at 7 o'clock in the morning, it was 25-degree ambient. 48 hours later, you can't come 7 o'clock in the morning because you have a meeting, so you have to come 1 o'clock in the afternoon, just after lunch. And the temperature is 37 degrees because it's summer. Then you notice when you look at the gauge, the reading is slightly different. So this is where the perfect gas law comes, because according to perfect gas law, we say P1 V1 over T1 equal to P2 V2 over T2. So for example, when you come to pressurize in the morning, it was 25 degrees Celsius ambient. And 48 hours later, you come in the afternoon, just after lunch, the temperature is 30 degrees Celsius. P1 here was 3800 Pascal. The volume of the system is the same, so we can cancel them out. So we can simplify this, become P1 over T1 equal to P2 over T2. Now we can predict what is the P2 gonna be at 37 degrees Celsius. It's very handy, isn't it? So rather than arguing with the subcontractor why there is a fluctuation of the gas reading, you can work it out yourself. And this formula is very handy when I did that project. Let's have a look different application of this formula here. Back to this. Let's have a look at an example. 5.1. So we have a gas volume of 4 cubic meter. I'm just going to draw like that. It's a gas, it's unknown. We assume it's perfect gas. The volume is 4 cubic meter. The temperature is 120 degrees Celsius and the pressure is 25 kPa gauge. So if this gas is at the normal atmospheric conditions, which is 20 degrees C and 101.3 kPa, what would be the volume? Okay, close that. Back to here. Now, first thing first, remember we have to convert everything to absolute. Let's label this as a condition number 1 and let's label this as condition number 2. In here you have P1, 25 kPa gauge, so we have to add 101.325 kPa. So 126.3 kPa now is absolute, no longer gauge. Temperature at 1, we need to convert the degree Celsius to Kelvin. So 120 degrees C plus 273 equal to 393 Kelvin. Do the same with P2. So 101.3 kPa, that's an absolute pressure already, so we don't have to do anything. Remember, the absolute pressure is what is the actual pressure that we are now being subjected by our atmosphere. If we have a gauge pressure in our hand, it will read 0. But in fact, we are being pressurized by the atmosphere by this much of pressure. Okay. Same with T2, we have to do conversion because this is still on degrees Celsius. So you add 273 that become 293 Kelvin. Now, the general gas equation say P1 V1 over T1 equal to P2 V2 over T2. So let's put everything inside. So P1 here is 126.3 kPa multiplied by 4 cubic meter divided by T1 393 Kelvin equal to P2 101.3 kPa multiplied by V2, which is we are after, divided by 293. Now you don't have to convert this into Pascal as long as on both sides you use the same unit. So if on the left hand side you use kPa, make sure on the right hand side you use kPa. But if you use Pascal on the left hand side, then right hand side have to use Pascal. Clear? So solving this math, V2 equal to 3.72 cubic meter. So as you can see here, when the temperature is 120 degrees Celsius, the volume is slightly more than when the temperature is at 20 degrees Celsius, which is true because when the temperature is lower, then the gas contract. When the temperature is higher, then the temperature expand. Let's have a look the next example. Let's clear the board. Example 5.3. So in this example, we have a compressed air tank, which is typical. So we have a tank. Oops. Draw a tank. So the tank here is 300 diameter and it is 2.5 meter long. So you fill this tank with the air, and after it fill, the gauge here indicate 1 megapascal gauge. Atmospheric pressure is 101.3 kPa and atmospheric temperature is 20 degrees Celsius. Calculate the mass of the air in the tank. So to solve this problem, what we're going to use? We're going to use equation of the state. You remember the equation on the state is PV equal to mRT. Now remember, we have to use absolute pressure here. So we need to change this gauge temperature, sorry, the gauge pressure into the absolute pressure. So we're going to convert that. And what else we need to convert? We need to convert the temperature into Kelvin. So if I convert this to Kelvin, I just need to add 273, come 293 Kelvin. To convert this, remember, we need to unify the unit. At the moment is 1 megapascal. So what we'll do, we say 1 megapascal is 1000 kilopascal. Oops. Sorry. You go. Plus 101.3 kPa. Now the unit is unified. So is 1000. 1 to the power 3 is 1000. So it's 1101.3 kPa. Absolute. Now we have the pressure here, which is the pressure of the atmosphere. We have the temperature, which is the atmospheric temperature. We don't have R. R of the air is given in your formula sheet. So R for A is, let me check, 287 joule per kilogram Kelvin. So rearranging this formula, mass equal to PV divided by RT. So mass equal to, we already calculate the P, the pressure of the air inside the tank, which is 1101.3 times to the power 3 Pascal now, not kilopascal, is on Pascal, multiplied by, oops, we haven't calculated the volume. So how do we calculate the volume of the air? Remember this formula of the circular or cylinder volume is not on your formula sheet. So to calculate the volume of the cylinder, which is my favorite, quarter pi d square multiplied by the length of the cylinder. So in that case is quarter pi 0.3, not 300 mil, 0.3 meter square multiplied by 2.5 meter long of the cylinder. So the volume is 0.1767 meter cube. Now we're going to put the volume here, 0.1767 cubic meter divide by R, 287 joule per kilogram Kelvin, multiplied by the temperature will be the temperature of the atmosphere, because the temperature of the tank is not given, so we assume the temperature of the air inside the tank will be the same as the temperature of the atmosphere. So 293 Kelvin. So mass equal to 2.314 kilogram. Mass of air inside tank. Now be careful here as we discuss the unit. So we made the conversion from kPa to PA, so you have to multiply by 1000. Same in here, we make the conversion from 0.3 meter to 300 millimeter. Okay, so these little details here, please pay attention. This one too, so it's megapascal. We multiply by 1000 to get kilopascal, so it can be added to 101.3 kPa. You can do whatever you like if you know what you're doing, but my suggestion, if you confuse, try to stick with one particular unit, then you never get wrong. So that's the answer. Next, we're going to discuss multiple process in gas. So the reason we discuss this is because next week we're going to have a look closely how the internal combustion engine will work, which is going to follow some of these processes. So for just today, we're going to discuss individual process quickly, and in next week we will piece it together, and we will look an example of internal combustion engine. The first gas process, what we call very simple, is constant pressure. So because it's constant pressure, the graph is kind of like that. So the pressure is always constant. It can go there. So the volume getting bigger and bigger and bigger if you go to the right hand side, which is expanding, or it can go there when the volume getting smaller and smaller. So it's compressing. If you imagine this is 0.0, that's 0.10, that's probably makes sense for you. This 0.0, let's say pressure is 5, so it's always constant at 5, but the volume expanding from 0 to 10 or from 10 to 0. So this is a constant pressure. The next one, we're going to have a look at constant volume process. So constant volume, we just go like that. So the volume is fixed, say 10, 3. So the volume is always 3, but the pressure changes. Now, to put it into context for constant pressure and constant volume, in the constant pressure, if you imagine a cylinder with a piston in it that goes up and down. So when the gas at the bottom is heated, so when the heat coming in, the piston will slowly goes up and goes up and goes up. So the volume goes up and goes up and goes up. But the pressure is always the same because it's open to the atmosphere. On the contrary, when the heat is being removed, the gas contract, the piston goes down and goes down and goes down. The volume getting smaller and smaller and smaller, but the pressure is the same. In the constant volume, the boundary is closed like that. So there is no change in volume. The volume is always the same. So when you supply heat into it, because the volume is the same, then what happens is the pressure goes up and goes up and goes up. If you cool it down, the volume is always the same, but the pressure goes down. Think your pressure cooker at home. Pressure cooker is not completely sealed because you have to let some pressure off, otherwise there is a risk of explosion, but the analogy is similar. So pressure cooker is a constant volume device. You supply the heat, the volume is the same, the pressure is getting higher and higher, and your lovely meat or chicken become tender under the pressure and cook faster, because as the pressure increase, your boiling water temperature increase above 100 degrees Celsius. So you have more heat into your meal. So your meal cook above 100 degrees Celsius. Okay. The next process, which is hard to tell, is what we call constant temperature process. So it's kind of like that. And the equation is PV equal to T. So this curve is governed by PV equal to T equal to constant, but because T is constant, then you don't need T. So it's only P times V equal to constant. The way you imagine it is the same like constant pressure, but instead of this piston moving nice and slow in a constant temperature, when you put the heat, it goes up very quick. If you remove the heat, it goes down very quick. The picture representation of it is very hard to imagine, but if you imagine a rifle, so there's a gun. Apologies for this childish representation, but when you fire the bullet travel from here, 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 and leaving the gun barrel very quickly. So thermodynamically, this is isothermal process. So for a few seconds, this barrel will be the same temperature, although after that, when you hold it, it's a bit warm or hot after multiple shooting. But at that particular second, when the bullet travel very quickly, the gas expand very quickly, then that is isothermal process or constant temperature process. The next one we going to look is what we call polytropic process. So polytropic. So polytropic process is when pressure, volume, and temperature all changes. This curve is governed by the equation PV to the power n equal to constant, while n here, n is polytropic index. Now in your exam, the n or polytropic index will be given to you, so don't worry about that. The last one that I want to discuss is adiabatic process. So in the adiabatic process, the curve is the same as the polytropic. So we still have P, we still have a V here. Oops. Let's get rid of that. Back to there. So in polytropic process, it's the same, like that. Now instead of PV to the power n, we have PV to the power gamma over C. Well, this gamma is what we call adiabatic index. Adiabatic means is isentropic or is constant entropy process. The pressure still changes, the volume still change, and the temperature still change. Okay, but the difference is in adiabatic process there is no heat involved. It is very hard to imagine. We will closely have a look this probably in the work example. So let's do a quick example on individual process so you know what we are after. Let's have a look example 5.7. So the question 5.7 is clearly say is polytropic process. So you don't have to think twice. What I'll do, I'm just gonna quickly transfer here. So the question defined is expansion because as you can see at point 1, the pressure is high, the volume is small, and as we go to point 2, the volume is getting bigger or expanding. So let's read the question. After ignition of fuel mixture of top of the stroke of an internal combustion engine, so that's point 1, the hot gas, so there is a gas here at point 1, the volume of the gas so at point 1, the volume of the gas, so V1 is 0.01 liter. Temperature at 1 is 1500 degrees C, and the pressure at 1 is 7 megapascal. The gas expands polytropically. The N is given as 1.5, so that's your polytropic index. To the bottom of the stroke, which is 0.2, compression ratio is 10 to 1. It's given gas CV or gas constant is 0.72 kilojoule per kilogram Kelvin. Oops, CP also given. So CP is 1 kilojoule per kilogram Kelvin. We have to find the temperature and pressure here. So question A is asking for temperature 2 and pressure at 2. Now the polytropic is the formula to do the polytropic isothermal adiabatic constant pressure, constant volume is summarized here. It also being summarized in your formula sheet as well. So you will have two for comparison. So what we're looking here is polytropic. We can say T2 over T1 equal to V2 over V1 and minus 1. So there's a relationship between pressure, volume, temperature. If we need to find out what is the work being done, use this formula. If we need to find out what is the internal energy change, we use this formula. If we need to work out what the heat being transferred, whether it's loss or gain, we use this formula. It's pretty neat formula, hey. So back to this equation here. Remember, we have to work on the absolute temperature and absolute pressure. Before you answering this, let's do quick conversion there. I'm just going to convert this liter to cubic meter, so we don't have to calculate later. So it's 0.1 liter. You have to multiply by 10 to the power negative 3 to get cubic meter. So multiplying by 10 to the power negative 3 means it's divide 1000 or divide by 1000. This one you add plus 273 to get into Kelvin. So it's 1773 Kelvin. P1 you have to now if you look the question closely, open the question again. The question said is 7 megapascal absolute. So we don't have to convert it to absolute by adding 101.3 kPa. But we need to synchronize the unit. So what I'll do, I'm just gonna make it into 7,000 kPa because we work on kilopascal, right? So 7 megapascal is 7,000 kPa, or multiplied by 10 to the power 3. Compression ratio 10 to 1, which is mean V2 is 10 times of V1. Is that right? So V2 is 10 times more of V1 because V2 is 10 times more bigger than V1. If we rearrange this, we can say V2 over V1 equal to 10. I will save this because we're going to use it later. Now we are ready to tackle question A. Let's have a look the formula. Here, from the formula, I'm going to use T2 over T1 equal to V1 over V2 to the power n minus 1. So we're looking for T2. We know T1 is 1773 Kelvin. V1 is 0.1 times to the power negative 3. V2, remember we discussed V2. V2 is 10 times of V1. Alright? So we can say V2 is oh, I made a mistake. Sorry. Just make it simple. We know V1 over V2. Oh, sorry. I mean we need to do V1 over V2. We know V2 over V1 equal to 10. So if we reverse this, V1 over V2, then we can say 1 over 10. So V1 over V2, the answer is 1 over 10. N we know is 1.5, negative 1. So you need to put it in calculator. 1 over 10 to the power 1.5 minus 1. So you put this on your calculator, you will get the answer. Solving for T2, we have 561 Kelvin. If you want to convert it, it's 288 degrees Celsius. So you can see here, we start at 1500 degrees Celsius. Now we're going down quite a lot to 288 degrees Celsius. So that's temperature at point 2. We need to calculate the pressure at point 2. Now if you look in here, PV, or pressure times volume to the power n, equal to constant. So what we can use either we can use that, or we can derive, which is make life more easier. So P1 V1 to the power n equal to P2 V2 to the power n. And we just say P2 equal to P1 V1 divided by V2 to the power n. So I simply arrange that. So P2 equal to P1 times V1 power n divided by V2. Now we know V1 over V2 is 1 over 10, right? And we know P1 is 7000 kPa. And we know n is 1.5. So solving for P2, we got 221 kPa. And this is already in absolute because 7000 kPa here is already in absolute according to the equation. So that's equation A. Let's have a look equation B. So what's the equation B? Equation B is asking the work transfer during the stroke. We are in polytropic and we want to calculate the work transfer. So we're going to use this formula. Just going to wipe my board. So we're looking for question B here. It's asking work transfer. According to the formula, work equal to P1 V1 negative P2 V2 divide n minus 1. We know P1 is 7000 kPa, V1 is 0.1 down to the power negative 3 meter cube. P2 we did calculate it before, is 221 kPa. V2, you have to calculate V2. So if V2 is 10 times V1 and V1 is 0.1 to the power negative 3, then what is V2, 10 to the power negative 3, isn't it? Cubic meter. Divide n, rather 1.5 negative 1. Now the result is positive 957 joules. So positive means work out. So if you got negative here, means the work is into the system. But yeah, positive is work out, which just makes sense because it's after the combustion, it's push the piston down to 0.2. So there is a work by the piston that being produced by the system. Okay. That's question B. Let's have a look at the next question. Question C. The internal energy change during the stroke. So back to this formula, polytropic internal energy change, we have to use M multiplied by CV, not CP, CV, and the temperature after T2 minus before 1. Delete my board again, or C. So C, internal energy change, so is U2 minus U1. The formula is U2 minus U1 equal to mCV T2 minus T1. Before substituting everything in this equation, we need to calculate the mass because we haven't done the mass. The information that we have to calculate the mass is on point 1. So if we use P1 V1 equal to mRT1, we can calculate the mass. Now the R here is given is 0.28 kilojoule per kilogram Kelvin. P1 is 7,000 kPa. That's 10 to the power negative 3. Sorry. So V1 is 0.1 times the power negative 3 equal to mass multiplied by R multiplied by T1, which is 1773 Kelvin. So mass here 0.000141 kg. So now we know the mass. We put the mass here. 0.0141 kg multiplied by CV. So CV is 0.72, 0.72 kilojoule per kilogram Kelvin multiplied by T2 minus T1, which is 561 Kelvin minus 1773 Kelvin. So the result here is actually a negative 1.23 kilojoule which means negative is decrease in internal energy. Now, apart from my messy writing, you need to pay attention on this unit. So this is kilojoule. So kilogram and kilogram is cancel, Kelvin, 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 cancel. Because it's kilogram, we need to, sorry, it's not kilogram, it's a kilojoule, then the answer must be in kilojoule. If you use joule, which is 0.72 multiplied by 1720 joules, then the answer here is 123 joules, not kilojoules. So make sure your unit are the same. The last question, question D. Oops. The heat flow from the cylinder during the stroke. So back again, polytropic heat flow, we're going to use this formula. On my board. So question, change color first. Question D is heat flow. Q minus W equal to U2 minus U1. If you remember from term 1, Q stand for heat energy, W stand for work, and U is internal energy, so U2 minus U1 is internal energy. Now what's the heat flow? We want to know what's the Q. So Q negative 0.957. Remember, we already calculated that it was positive before, so positive times negative will be negative. If this work is negative, then it's negative times negative become positive. Is that clear? Don't change this sign. This sign is negative, is always there. Don't change it to positive. You only change the sign of the work, whether it's work input or work output, equal to negative 1 to 3 as we calculate before, because it's losing energy. So we can say Q, because negative, positive, negative, then this negative move to the other side, become positive, so 0.957, negative 1, 2, 3. So Q equal to negative 0.273. So the negative sign here indicate heat flow out, which is true because if you remember, the original temperature was 1500 degrees Celsius at point 1, and at point 2 here the temperature at point 2 is 288 degrees Celsius as per question A. So we are losing the heat energy here. So this sign is consistent. So that's how you check your answer. If you know you're losing energy there, and then this answer here is positive, then you know you're doing something wrong. It has to be consistent. Okay, I think that's the end of the work example. Now I have scanned some of the examples here, which is I want you to practice at home. So what we'll do question 5.2, 5.5, we'll do 5.62, 5.7, and then let's say 5.12, 5.14, 16, 19, and 25. Oops, let's save that. What I'll do in this recording, I will try to do some of the question and the rest you could try yourself at home. If you have a book, you can open your book, but as you know, there's always an answer at the bottom. So let's have a look question 5.2. 5.2 is similar what we did before, so I'm just going to do quickly. This is a cylinder. Internal diameter is 1.2 meter. It's a pretty big cylinder. The length is 2.8 meter. It's filled with air, and the pressure gauge reading 150 kPa gauge. So that's a pressure gauge. What is the mass of the air? If the air temperature is 15 degrees Celsius. So again, to conversion, so PA 150 kPa plus 101.325 kPa you'll have 251.325 kPa. Oops. But now it's absolute. The temperature of the air is 15 degrees C plus 273. So you got 288 Kelvin. We're going to use this formula, PV equal to mRT. R for air is 287. So that is given on your formula sheet, and the unit is joule per kilogram Kelvin. So 251.325 kPa multiplied by the volume, which is we need to calculate again, sorry, forgot. So the volume of the tank, quarter pi t squared times the length. In this case it's already in meters, so we don't have to convert it again. So 1.2 meter square multiplied by 2.8 meter long. So if you put in calculator, 1.2 square divided by 4 multiplied by 3.14 multiplied by 2.8 is 3.165 cubic meter. So you put it here, 3.165 cubic meter time equal to mass of the air multiplied by 287 multiplied by 288 K. So it is joule per kilogram Kelvin. Solving this equation, the mass equal to 8.249 kilogram. Okay. I will skip 5.5, 5.6 similar, 5.7 similar. Let's do 5.12. Close this window. 5.12. Clean the board. So 5.12 move it there a little bit. So we have a cylinder. So we have a vertical cylinder like that. We have a piston and it contains an air here. Now the question is not really straightforward, so just bear with me a second. What happens is when the heat energy is supplied to heat up the air, then the piston raises by 300 mil. The question is also asking to neglect the friction. Now to calculate the absolute pressure of air in the cylinder, we have to calculate the volume of the final volume of air and the final of the piston position here at 300 mil. Now the tricky bit is we do not really know what is the original position of the piston. So it's not really straightforward. So how we do that is to calculate the initial volume. We're going to use PV equal to MRT. Let's say initial volume is 0.1, so P1, V1, M1, T1. The question says is open at the top, so that's open at the top, hence is exposed in atmosphere. So P1 here will be the absolute pressure of the atmosphere, which is 101.325 kPa. V1 is what we're looking for. Now the mass of the air is given is 0.005 kilogram. The R of the air 287 joule per kilogram Kelvin, and the T, remember, is 288 Kelvin. So 288 Kelvin. Now if you look in here, back into this pressure again, the pressure of the air here is contained of two pressure. So one, the pressure due to the atmospheric, so you got atmospheric pressure here pushing these things down, and you also have the pressure of the piston, right? So due to the piston, how do you find the pressure due to the piston? If you remember, pressure equal to force divided by the area, and force here is m mass times gravity divided by the area. What area here? This is the surface area of the piston, of course. So the piston has a bore of 100 mil, so that's the area of the piston. The mass here would be the mass of the piston, which is 15 kilos, and the gravity is constant. So that's 15 kilogram times 9.81 divided by quarter pi is 100 mil. Remember, it's 100 mil, so we have to convert into meter square. Okay. So 0.1 square multiplied by 3.14 divided by 4. 15 multiplied by gravity divided by answer. So we have 18.74 Pascal. So in here, the P, we have 18.74 multiplied by I think to make life easier, what I'll do, I'm just gonna I'm just going to convert the kPa to Pascal to make everything easier. Then we have converting kPa to Pa, and or Pa to kPa and doing it again. Sorry about that. Start again. So P is the atmospheric pressure. I'm just going to 101,325 Pascal plus this, the piston, 18.74 Pascal. So we have Pascal, Pascal, we are after phi1, that's equal, we know everything. Okay, so solve for this. Phi1 or equal to 120070.22 divided by 413.28, so 3.44. Sorry, the other way around. So again, so view 413.28 divided by 120070.22, so 3.44 multiplied by 10 to the power negative 3 cubic meter. So this is phi1. Now we know, and then now we have to work back to find the length. So phi1 equal to quarter d square multiply the length. So 3.44 10 to the power negative 3 cubic meter equal to quarter 4 d squares time length. And length is 0.4384 meter. So finally, new volume would be phi equal to quarter pi d square 0.438 plus 0.3. You see what we are trying to do here? We try to calculate this volume of air here. The only problem we only been given is moved by 300 mil. So we don't know what's the original position. So by doing this backward calculation, we established the original position was 0.438 or 438 mil. So that's the original position. And then from that 438 mil, it's moved by 300. So the final volume is this, 0.438 meter plus 0.3 meter. So the final volume is 5.79 multiplied 10 to the power 3 cubic meter. So that is the volume here after the piston been moved. Is that clear? I'm sorry, a bit messy. Now we can calculate the the absolute pressure in the cylinder. So let me clean the board. I'm just going to record what we have. So we established the volume of A, 5.79 10 to the power negative 3 cubic meter. So equation A, the absolute pressure of the air in the cylinder. So to calculate the absolute pressure, P2 V2 equal to mRT2. So volume 2, this 5.79, P2 is asked. Another problem is T2. We don't know what's T2. The question only give us T1, which is 15 degrees Celsius. So before we substituting this, let's calculate the T2. This is the cylinder open to the atmosphere. If you remember from the early discussion, when the piston is open to the cylinder, the pressure is always constant. Alright? So we know P1 V1 over T1 equal to P2 V2 over T2. Now because the cylinder is always open to the atmosphere, so regardless where the piston here or the piston at the bottom is always has the atmospheric pressure, and the piston here is constant, is 15 kilo. So we can delete P here because it's the same, so it's cancelled. So we only have V1 over T1 equal to V2 over T2. We calculate V1 before, remember? If you go back in few minutes ago, V1, we calculate as 3.44 times the power negative 3 cubic meter. T1 is 15 degrees Celsius. We have to convert that to Kelvin. So it was 288 Kelvin. V2 here. So I just put the V2. 5.79 10 to the power negative 3 divided by T2. So solve for T2. We have 485.24 Kelvin or 202 degrees C. Now we can substitute everything into this equation. So P2 we are after, V2 is 5.79 to the power negative 3 equal to M in here is mass of the air. So mass of the air is 0.05 kilogram. R of the air is 287 joule per kilogram Kelvin, and T2 here is 485.24 Kelvin. So solve for P2 is 12137.26 Pascal or P2 is 120 kPa. So that question A. So remember, this is constant pressure. Okay. So question B, the heat energy being supplied, you just need to go up here, constant pressure for the heat energy. The formula is this, mCp T2 over T1. Let's clean that. So question B, heat energy. Heat energy being supplied. So it's constant pressure. So Q mCp T2 minus T1. Again, mass of the air 0.05 kilo. Let's go back to the equation. Mass of the air 0.05 kilo. Now Cp of air, if you look on your formula sheet, is 1005 joule per kilogram Kelvin. Pay attention on this. Multiply by 485.24 minus 288 Kelvin. Capital K. So the Q here is 991 joule positive. Remember, this is joule, so the final answer is joule. Positive mean heat input. Is that clear? So that's question B. Question C, the change of internal energy. Back to this formula. Constant pressure, change of internal energy instead of Cp, now it's Cv, but it's the same formula. So C delta U Q equal to mCv now, T2 minus T1. So it's the same with this, but Cv for air is 718 joule per kilogram Kelvin. So Q equal to 708 joule positive, means increase in internal energy. So I don't put the value of T2 and T1 because it's the same and the mass is also the same. Okay. Question D. The work done by the air in the cylinder. So look, constant pressure, the work being done is that formula. Just clean the board again. So question D, work done equal to P V2 minus V1. So the pressure here will be the final pressure, the P2, which is we already calculate. So the P2 was 1270.22 Pascal. Then we did calculate V2 was 5.79 10 to the power negative 3, negative 3.44 10 to the power negative 3. So work done is positive 282 joule. Mean work out. So the work is being produced by the system. Okay, so that is one of the question. The last question I want to discuss before we finish is question 5.25. So question 5.25, it says is a mass of air is compressed isothermally and then constant pressure and then expand adiabatically. So there are three processes here. If you draw it in PV diagram, so the first step, compress isothermal. So isothermal, kind of like that. So that's point 1, that's point 2. So say V1, V2, P1, and this is a P2 here. So the volume has been compressed isothermally. So the volume here from V1 to V2 is getting smaller and smaller, and the pressure is getting bigger and bigger. So this is an isothermal compression. I'm just gonna use different color now. After that, the heat is added at constant pressure. So there is an addition of heat there at constant pressure. Then the final one is expand adiabatically. So from here to here. So let's say this is point 3 and that's final 4. So 1 to 2 isothermal, 2 to 3 constant pressure, 3 to 4 adiabatic. So that's a compression. This is a heat addition, and this is expansion. Is that clear? Now let's have a look at the equation. So the air mass, so mass of the air is 1 kilogram. Temperature here, 20 degrees Celsius, is temperature at 0.1. So we will say 293 Kelvin. Now remember, from point 1 and point 2 is isothermal compression. Isothermal means constant temperature. So we can say here T1 and T2 is actually the same. So T1 and T2 is 293 Kelvin, okay, because it's isothermal. The next one is compressed isothermally to pressure of 400 kPa. So we can say P2 is 400 kPa, P1 is 100 kPa. Now this question here, I'm pretty sure if you look closely, oops, gas pressure are already in absolute unless gauge pressure is stated. So P1 and P2 here is already on absolute pressure. We don't have to convert them anymore. The next information, heat being added here. Is 100 kilojoule. So 100 kilojoules being added. And then after that is adiabatically expand to 4. Now, question A. The work that being transferred during compression. So remember 1 to 2 isothermal compression. So scroll up, find isothermal here. Work being transferred is this formula. So A work equal to P1 V1 ln V2 over V2. So this is isothermal. Do we have all the information? Well, we have P1. We don't have V1 and we don't have V2. So we need to find V1 and V2. So let's find V1 first. We use this one. P1 V1 equal to mRT1. So P1 is 100 kPa multiplied by V1 equal to the mass of the gas. I think it's a 1 kilogram. Just going to check. Yes, it's a 1 kilogram of air. So the mass is 1 kilogram. R is 287 joule per kilogram Kelvin, and T1 is 293 Kelvin. Solve for V1. V1 is 0.84 cubic meter. Next one, to calculate V2, we can use P1 V1 over T1 equal to P2 V2 over T2. Now because it's isothermal, the T is the same, so we end up with that. So we know P1 is 100 kPa multiplied by V1 is 0.84. V2 is 400 multiplied by V2. So solve for V2 is 0.21 cubic meter. So now we know V1 and V2, we can solve this. So work being transferred, P1 is 100 kPa, V1 is 0.84 ln V2 over V1. So to calculate this, you put in calculator ln bracket 0.21 divided by 0.84 bracket, and then it will give you the answer. The solve for work is negative 116.44 kilojoule. Now why is negative? Because it's work in, which is makes sense because you need a work in order to compress the gas. So the system need a work, hence is negative sign. Okay. Question B, the temperature after the heat being added. So where is it? So the heat is being added from 2 to 3. So the heat that being added is at 3. Let's clean the board. Question B. Will be T3. So what's T3? So 2 to 3 is constant pressure. So if we use P2 V2 over T2 equal to P3 V3 over T3. Now because it's constant pressure, then the pressure 2 and pressure 3 is the same. So we are left with this equation. So V2 over T2, V3 over T3. We already calculate V2. So 0.21 T2, we calculate T2 before, which is the same with T1, 293 Kelvin equal to V3. Now we don't know what T3 is, isn't it? So we need to find, oops, sorry, I think I jumped to question C already. So that's question C actually. Jump too quick. This is question C. Okay, leave this one for time being. Let's back to question B. So question B, what is T3? So question C was work transfer. So back to question B. So what's the T3? Is a constant pressure. Let's have a look. Constant pressure, constant pressure. So we know the heat being in, we know the mass of the air, we know Cp, we can calculate T3. So we can go here, so Q equal to M Cp. Now it's always final minus initial, so T3 minus T2. That's 1 kilogram. Cp for air is 1005 joule per kilogram Kelvin multiplied by T3 negative 293. So 293. What's happened here? Oh, 293. So solving here, the Q is 100 kilojoule. Remember, it's positive because it's being added into the system. So we can solve T3 is 392.5 Kelvin or 119.5 degrees Celsius. So that's question B done. Let's have a look at question C. So question C is asking for the work transfer during the adiabatic expansion. So the work transfer between 3 to 4. So let's have a look at the adiabatic expansion. So adiabatic here work as the similar with polytropic except change n into gamma. So change polytropic index to adiabatic index. So we're going to use this formula here. Let's keep this white. Just going to write it down here. So equation D 3 to 4. So W equal to P not 1 P3 V3. Remember, look at the formula is initial minus final negative P4 V4 divided by minus 1. So what do we know here? We know P4 equal to P1, which is 100 kPa. We need to find V4. We need to find V3. We know P3 equal to P2, which is 400 kPa. So to find that, we need to use this formula. Let's find V3 first. So to calculate V3, I think the easiest is to take the relationship between 2 and 3, which is constant pressure, which is I've done here. So V2 over T2, V3 over T3. Now T3, we calculate that before. So I'm just going to put the number 392.50. So solve that. V3 equal to 0.281 cubic meter. So we got P3, we got phi3. We need to find phi4. So phi4 is the relationship is between 3 to 4, which is the adiabatic. So let's have a look adiabatic there. S for polytropic, except N change to adiabatic. So let's see here. What I will use is this expression. This is on your formula sheet, not on the summary that I have. So P3, sorry, P4 over P3 equal to V3 over V4 over to the power gamma. So what's the polytropic index here? It's not adiabatic index. Okay, so adiabatic index here is not given, but I'll give it to you. The adiabatic index here is gonna be 0.4. So in exam, this will be given to you. I think in this equation, I have to calculate it. So P4 is 100. Remember, P4 and P2 is the same. So P1 here, P4 also here. Okay, so that's the same. So P1 and P4 is 100. P3 here and P2 here, they are the same, which is 400. V3, we have that 0.281 to the power 0.4, and V4. V4 equal to 0.756. I'm going to explain how you take V4 out this equation in a minute, so just bear in mind. So we have V3, we have V4, we have P4, we got everything, so we can solve off this equation. Now I'm going to leave that to you. So P3 is 400, put it here. V3 is 0.281, put it there, and then put P4, V4 gamma. So the final answer is 92.1 kilojoule. Okay. The final volume, which is V4, you already calculated 0.756. So that's question D, rather. Now, mathematic expression, how to convert that. Just quickly, here is this. So what happened, we have something like this before. How do you extract V4 out from the equation? Well, the easiest is actually to multiply this with the opposite side. What I mean is like that. So I'm just gonna delete 0, 0. So it's 1.4, 1 over 4. 1 over 4 equal to 0.281 over V4. So what I'll do, because this is to the power 0.4. I'll just multiply this by 1 divided 0.4. So that and that cancel, become 1. But you have to do the same thing. So you have to do to the power 1 over 0.4 on the other side. So this becomes 0.25 to the power 1 over 0.4, which is you can solve your calculator, and this is 0.281 over V4 without any power, right? So you can solve that. So 1 divided by 0.4 is 2.5. So 0.25 divided by 0.25. So 0.71 if you solve this in calculator. So to solve V4, simply multiply simply by 0.281 divided by answer. So it will give you the answer. Sorry, I think I made a mistake. The adiabatic index, not 0.4, is 1.4. So apologies for that. So please change that on your previous calculation. So again, I repeat, adiabatic index is 1.4. That's why I got a weird number there. So 1 divided by 1.4, 0.25 to the power of that. Yeah. So you got 0.756. So V4. 1 divided by 1.4, 0.25 to the power of that. So that one is 0.37. Okay, apologies about that. Sorry for confusion. That's it for today. We'll finish up to here. So next week we're going to discuss more about the gas processes in internal combustion engine, which is most likely going to be involving 3 or 4 processes like that, and that is something that we kind of expect in the exam as well. See you next week.